Now that we've got limits defined on vector-valued functions, let's look at derivatives and integrals of vector-valued functions. First up, differentiation. I'm going to use the two-dimensional version of this. Higher dimensions are completely analogous. Let's say we've got some vector-valued function r of t, and we'll define this to be r1 of ti, so it's got an x-coordinate and a y-coordinate. And I want to identify what the derivative of this is. Well, the definition of derivative is the same as it is in Calc 1. The definition of derivative is the limit as h goes to 0 of r of t plus h minus r of t divided by h. So it's like the idea of slope of the tangent line, although slope maybe doesn't mean exactly the same thing that it used to, but it still represents the change in r. Think of this like the change in r divided by the change in the t value. Yes, that's what our derivative is sort of representing. So if we were to write out what this means, well, let's put in our definition of r. So this is the limit as h goes to 0 of r1 of t plus h, r2 of t plus h, minus r1 of t, r2 of t. Right, we're just writing out the components of the first vector r of t plus h and the second vector r of t. Now we can combine those components together. We can add the x components and add the y components. So this gives us the limit as h goes to 0 of r1 of t plus h minus r1 of t divided by h. And then for our second component, r2 of t plus h minus r2 of t divided by h. And now, using the result we had at the end of the last section, we can apply the limit on each of these separately. So the first one is actually the definition of derivative of r1, and the second is the definition of derivative for r2. So what that says is that we can take the derivative component-wise. So for a concrete example of this, let's say we have the function r of t is t squared e to the 3t and cosine of 2t. Then our derivative, r prime of t, we just take derivatives component-wise. So we've got 2t, 3e to the 3t, and negative 2 sine of 2t. Right? We just take the derivative term by term. Now we define the integral just as sort of an extension using the inverse of derivative. So the integral of r of t dt, we'll just define this to be the integral of each of the components. The integral of the first, the integral of the second, and so on. So let's look at an example of this. Let's say we've got, let's do a motion problem. Let's say we've got our acceleration, is given by, say, negative 9.8. We know that, say, the velocity 1 second in is 2 meters per second, and we know that after 2 seconds, our position, I should call that r instead of s, our position will be, say, 2, 3, 4. This initial velocity, this velocity needs to be a vector, so we'll say 2, 1, 7. Okay, so so we've got this these three vector conditions on here. Let's go through and do some integration. First off, if we integrate acceleration, we'll get velocity. So the velocity will be the integral of 9.8. I should have said this is in the k direction. So all of these are vectors. So if I integrate this negative 9.8k, I get negative 9.8t, also in the k, plus some constant of integration. Now the constant of integration, it's important to remember that this is a vector. So now to figure out what that c is, we're going to take this condition here on v, and we're going to plug that into the equation we have so far. That means plug 1 in for all the t's and solve for c. So on the left-hand side of the equation, v of 1 is 217. On the right-hand side, we've got 0, 0, negative 9.8, plus c. Now if we solve this for c, we'll move the 9.8 over, and we've got 2, 1, 16.8 equals c. So we figured out what the c is after our first leg of integration. That means our velocity is now negative. Let me write it out in component form. So this is 2, 1, 16.8 minus 9.8t. So we've got our velocity. We want to find the position function, so we'll integrate again. So now we'll integrate both sides of this with respect to t. So the integral of velocity gives us position. We're just going to integrate component-wise. So the integral of 2 gives us 2t. The integral of 1 gives us 1t. And over here we've got 16.8t minus 4.9t squared plus a constant of integration. And again, that constant has to be a vector because we're dealing with a vector on both sides of the equation. And now we're going to plug in our second initial condition on here. So we're going to plug in 2 for all the t's. So on the left-hand side of the equation, we get 2, 3, 4. And on the right-hand side of the equation, we're plugging 2 in now for all the t's here. So this is going to give us 4, and then 2. Now here we're plugging 2 in for both of these t's. So this is going to be 16.8 times 2 is 33.6. And then over here, if we're plugging 2 in for t, we're multiplying this by 4 now. So that's going to be 19.6. We go and subtract those two, and we've got 14. Okay, plus the c. So now we can go and subtract this from both sides to solve for c. So we know that c is now negative 2, 1, negative 10. And we're finally ready to summarize that equation we have for r. So r is then 2t minus 2, 1t plus 1, and then negative 10 plus 16.8t minus 4.9t squared. And that's integration and differentiation of vector valued functions.